Okay, so this is our first example of friction, and we will do the example of a box, and the question is it tipping or is it slipping? And what is the lower force P to begin to move the box? And when we say move the box, move is either, oops, that's so big, either slipping or tipping. Okay, so we will solve for both. Let me just write the information that we get. The weight, so the weights apply at G. Okay, that's your weight, and it's equal to 250 pounds. And the mu s that we need, the mu s, is equal to 0.4. Okay, mu does not have any units. Okay, it's just between 0 and 1. Okay, so we have some space there. So I will go to the left, and I will do the slipping scenario. Okay, and to the right, I will do the tipping scenario. Okay, the free body diagram are different. If we do the free body diagram of the slipping, we have our crate. Let's try to do the kind of the same size. Okay, we have our crate. We have the weight in the middle that we know, and we have three forces that we don't know. We have the force P that we don't know. Yeah, I should put the weight a little bit bigger. Here we go. Okay, we have the force P that we don't know. We have the normal force that we don't know, and we don't know where it's applied. And what is the motion? The motion tends to be to the right because we push to the right. So your force friction is to the left. Okay, so that's your free body diagram for the slipping. For the tipping, so we have the same box, so the same size. Okay. We have the same weight in the middle. And we also have three forces that we don't know. We have the force P, and depending on slipping or tipping, that will not be the same force P. We have a force of frictions going to the left. And because it's tipping, the corner that stay in contact, let's call this as a point A. Okay, so at the point A, the contact is only between the corner A and the surface. So the normal force that we don't know is on the corner. Okay, so your free body diagrams are different if it's slipping or if it's tipping. Okay, in the case of tipping, we know where the normal force apply. It's at the corner. When it's slipping, we don't know where the normal force apply. Okay, to solve for P for slipping, what we will do, because it's slipping, we reach the maximum force. So we have the equation. When it's slipping, we know that the force of friction is max. Okay, and it's equal to mu s times n. Tipping, we don't know that. We don't know the force of friction because it's not slipping. It's tipping. Okay, so let's do the slipping. I will write the dimension that we need after. The first thing that we know, the only thing that we know is W. Oops, let me put it in blue. It's W. So what we can do the sum of the forces on Y, it's equal to 0 because we know W. Okay? So we have minus W plus N, it's equal to 0. So we find that N, it's equal to the W that is equal to 250 pounds. Okay, that's the step number 1. Step number 2, now that we know N, and we also know mu S, step number 2, we will use the equation of the maximum force of friction that is equal to mu S times N. Okay, so oops, let me make it a bit smaller. Can you see? So the force of friction, that is max because it's slipping, so there's some motion, so we have reached the maximum of the force of friction, of the static force of friction. So the force of friction is equal mu s is equal to 0.4 times n, that is 250. Okay, so we found that the force of friction is equal to, is it 100? 0.4 times 250. Yes, it's 100 pounds. Okay, so that was step number 2. Now step number 3, that now we know the force of friction, we can find P. How do we find P? We use sum of the forces on X, it's equal to 0. Okay, so we have P minus the force of friction, that is equal to 0. So the P is equal to 100 pounds. Okay. What does that mean? It means that if it's sleeping, no, it means that the bugs will begin to sleep if P is equal to 100 pounds. Okay. Not 100% exact. Let's do the tipping, and I will explain you one more thing after that. Let's do the tipping now. Okay. Tipping is easier. We just need one equation to solve for P. Okay. Why? Because we know the location of the normal force. It's at A. So look, if we do sum of the moment about A, it's equal to 0. What do we need? We need the distance between W and A. Oops. So we need this distance. That is 1.5. So this is 1.5 feet. Let's make it bigger. Here we go. So that's this distance. Okay, so the horizontal distance. And we need the dimension between P and A. So we need this distance. That is 4.5 feet. Okay, that's the vertical distance. Okay. So when we do sum of the moment about A equals 0, we have W that tends to rotate in the positive direction. So W times 1.5. And P then rotates in the negative direction, so minus P times 4.5. It's equal to 0. So we have P times 4.5, that is equal to, the W is 250, so 250 times 1.5. And finally, we found that P is equal to 250 times 1.5 divided by 4.5. It's 83.3 pounds. So it means that the force required to tip is 83.3, and it's lower than the force required for sleeping. So is it tipping or sleeping first? It will tip first because the force is lower to tip than to sleep. Okay, we need to check one thing, two things. Okay, we need to validate that. This is enough to say that it's tipping, but I will make a proof that it's not sleeping. If it's sleeping, the normal force is somewhere below the fridge, right? The box. Let's call that this distance x. So let's do the checking. We will check that it's not sleeping because we know it's not sleeping because it's tipping. So if we do, let's call this point the point O. Let's do the sum of the moment, not sum of the moment about O, sorry. Yes, let's do the sum of the moment about O, it's equal to 0 equation. Okay, that's the check. Okay, we can't see anything there, so let me move it there and let me make it bigger. Okay, I do the check. Check. Tuk tuk. Okay, if I do sum of the moment about O, it's equal to 0. Okay, I need some distance. This distance there between 0 and the W, I don't know this distance. So let's call this one x. And this distance, the vertical distance with P, is also 4.5. Okay. So sum of the moment about O equals 0. So we have plus, yes, W is plus W times the distance x that we don't know, minus P times 4.5. It's equal to 0. And the only thing that we don't know here is x because we found that P equal 100 when it's sleeping. Okay. So we have W, we have x that is equal to P, that is 250. No, P equal 100, sorry. P that is equal to, let me write, P times 4.5 divided by W. So x is equal to P 100 times 4.5 divided by the W of the crate is 250. And we find that x is equal to, so 450 divided by 250, it's 1.8. Okay, and here is the problem. 1.8 is more than the 1.5. That means that your normal force, in fact, is somewhere there, outside the box. So it cannot slip, because if it's slipping, your normal force is not anymore below the box. Okay? So this check should tell us that it's not slipping, it's not possible. Okay? We already know that because we proved that it was tipping first. But we just check that. And for the tipping, the check is, if it's tipping, the check is that the force of friction is less than the maximum force of friction. So let's find the force of friction. So we have the force of friction. If we do sum of the forces on x, it's equal to 0. We have P minus the force of friction, that is equal to 0. And we know P. So here our unknown is force of friction, because in the case of tipping, the force of friction is less than the force of friction max. Okay? So less than mu s times n. Okay, so the force of friction is equal to P, and the force of friction is equal to, for P we find 83.3. So it's equal to 83.3 pounds. And the maximum force of friction, the FF max, it's equal to mu s times n, and the mu it's equal to mu s times n, and the force of friction max is equal to 0.4 times n. And to find n, we need to do sum of the forces on the y equals 0. Okay, so sum of the forces on the y equals 0 mean that minus w plus n is equal to 0, so n is equal to 250. Okay, so if we come back on this equation, we have the force of friction max that is equal to 0.4 times 250, that is equal to 100 pounds. And yes, let's come back on this one. The force of friction is less than the force of friction max, that is equal to 100 pounds. So it means that we didn't reach the maximum force of friction, so the box cannot slide. So it's tipping, something that we already know. Okay, so let's try to summarize what we did. We did the scenario of slipping and the scenario of tipping. Okay. For both of them, we find the maximum force, P. Okay, and to find the maximum force, that's two different free body diagrams, and that's different equation of equilibrium. In the first case, slipping, we use force on x, force on y, and the fact that the force of friction is the force of friction max, that is mu Sn. For the tipping, we simply use the moment about A. Okay, we compare both pushing force, and the smaller force is the one that occurs first. Tipping occurs first. Okay, and to check that, we check that the distance between the normal force and the center of the box is more than half of the width of the box, so it's not possible. For the slipping, the check is to check that the force of friction is less than the maximum force of friction, and we check that you are finding the maximum force of friction, that is mu Sn. That is the term, not the slipping. Makes sense? And it's less, so yes, we didn't reach the maximum force of friction, so we didn't slide. Yes, we didn't slide because we tip first, because when we do the moment about A, the pushing force is lower than when we do the slipping equation. Okay? So take some time to review those steps and do the other example, and I will give you more examples during the live session to work on that. That's a key problem. Okay, and that's a bit challenging. So see you in the next video. Bye bye.